Or could someone get the door? Let's get started. Thanks. All right. So welcome to session 6 out of 8. So we're getting close to being done with this whole workshop or course or lectures, whatever you want to call it. So as usual, you start by going to the Git repository that you copy for this course and do the git pull upstream master. By now, it's starting to become part of your motor memory. And this is just to get all the updates I posted roughly an hour ago. Yeah, so it's fresh. And once you get the thing, I already got it updated, so you don't see anything on mine, but you should have things scrolling showing that there have been a couple new things added. Go ahead, start the Jupyter Lab. Yeah. You are not in the right place. You have to go change directory into the GitHub repository. So one of the folders that is the place you copied or cloned. You probably want to go to Documents and then Python Neuro 2018. Yeah. And let me just full screen this. Yeah, so given this session 6, there is a notebook called 06, Image Manipulation in Python. And that's what we're going to talk about today is as a continuation of the theme of using Python to work on data, since you already have learned quite a bit about the packages like NumPy for numerical array and Matplotlib for plotting. Last time we talked about how you can load things from files. It could be like new line separated files or comma separated values. Look at the pain of writing your own interpreter, owning your parser. That took quite a bit of work. But if you use functions provided to you, then it often gives you much easier time loading those files in. And you can even use NumPy specific file formats, which makes transferring NumPy arrays pretty straightforward. And we look at a couple of different ways to analyze it. Look at the statistics, plot the neural traces, and I even actually added the bonus section that I don't know if you had a chance to read, which is actually about like if you were to go about implementing something like spike detection, how can you go about doing it just using things you already learned, manipulating NumPy arrays. So with that, today we're actually doing another set of very popular modality in the field of neuroscience, or in fact just any computational field, which is images. Popular for many reasons. Like it's a pretty rich set of data. If you think about it, you have at least two-dimensional array that you're presenting, so it has a lot of way to present the data. And popular because it's very pleasing to be looking at. It's one of those things that if you do any analysis on, you can actually immediately make a plot out of it, and there's some visual pleasure to be looking at it. So if you can work on something like this, it's pretty nice. You can fill your screens with lots of pretty images, and also makes you feel like you're doing a lot of work because it looks impressive by itself. But aside from that, obviously there are many, many interesting things you can do with images, so we'll try to scratch the surface today. And there'll be some theme of this continuing with the next session, as I'll touch at the end of this session. So first thing first, you always import just packages that you know what you'll be using. So here I'm just importing NumPy as MP, and I'm also importing the Matplotlib PyPlot subpackage as POT, and also doing the Jupyter Magic %matplot inline to make sure all of my plots shows up inside the notebook. So go ahead and run that. Now, a couple sessions back, I already talked about how if you were to work at an image in Python, it could be as simple as just having some sort of a 2D array. Like any generic 2D array, more or less, can be considered as an image. So here, if I were to just create a 2D array of size or shape 32 by 32, so it's 2 dimensions, right? 32 by 32, that's a shape. I just created one. And if you use the Matplotlib's like image show, that's image show, you can already look at it. In this case, everything is filled with 1, so it's a one-tone image. There's nothing that impressive to be looking at it. Now, you notice that by default, it will put all the X and Y coordinates along with it. When you're just looking at images, oftentimes those exact values are not that useful, or it just makes the image look a bit dirtier if you have a lot of axis tick marks. So for pretty much all the plots we'll be generating this time, when you're looking at images, I'll actually turn the axis off. So that will actually just give you image by itself. So as I already mentioned, this is a 2D array standing for something that has both height and width. And this is actually the requirement for something to be considered as an image, is that it must be at least 2D array. Now I'll touch on like why is it at least very shortly, but if it's 2D array, then it has height and width and hence could be interpreted as an image. This also means if you have something that is a 1D array, for example here by creating a lin space that goes from 0 to 1 with 5 points total and call it gradation, if I try to plot that, it will error out because it doesn't have enough dimensions. So if you scroll all the way down, it says invalid dimension for image data. And this is because you try to plot something that has only one dimension. It has a hard time understanding how to plot it as an image. So if you want to get over that, one trick is to add a dimension. So you can still plot something that is otherwise a flat raw vector as long as you gave another dimension to it. And previously we already looked at one trick is to add a new axis. So if I were to turn this into this 1D array into something that's 2D array with one extra dimension prepended, I will do this np new axis trick to increase the dimension. And now I can increase show the image. And this is what you get. So here is basic gradation, changing color at least somewhat linearly across steps. So there are 5 data points, and that's what exactly you're seeing. Now, if you were to actually add the extra dimension on the as a second axis, so you're putting into the adding on the second portion to make it a column vector. If you were to plot this, then they will actually plot it as a column vector or column-wise image. Right? So it actually does correspond in terms of how it plots it. Now, one interesting thing that you can do with it, so here basically I've created an x, which is a raw vector, 2D array, and y, which is a column vector, which is still a 2D array. If I were to do something like multiply these two vectors together, as I covered some sessions ago about broadcasting, they will replicate the dimension that is in singleton dimension to eventually give you something that is full-fledged 2D array. And here can you just visualize it. So you say image is equal to x times y, and what you get is something that looks like this. And also here I just plotted what the actual content of the array looks like, right? I just showed it out. So this is just a result of doing, like, if you were to take the two vectors, a row and column, and do like position match-wise multiplication, this is what you get, and you can get a nice visualization just by plotting a matrix. So this is actually another way by which you can go about thinking about images, is that it could just be used to just visualize a matrix as well. If your operation involves coming out the 2D array, which is interpretable as matrices, it may be pretty nice to just look at the content, not just by having it number-wise like this, but by being able to plot it, you can get some sense of what the matrix structure looks like. Now, actually going along this theme, it is actually pretty common to think of 2D arrays, like these things you're seeing as images, to actually be representing some sort of a 2D functions. So 1D function would be something like this, where x equals MPA range, and we plotted a lot of this like couple sessions back, where I take an input and I just compute one number that corresponds to it, and I can just also plot f by itself, right? The 1D vector by itself. It will automatically use the index position as the x value. So this is a 1D plot or 1D function. If you have a 2D function, then instead of just having one input, x, as an input and y as the answer, you now have x and y as the input with the z, say, as an answer. So here, for example, what we plotted earlier when we multiplied two vectors could be interpreted as representing x times z equals x times y. Right? So, for example, like if I were to now do something slightly different, here I want to do x plus y divided by 2. What I could do is try to represent x, again, as a raw vector, and then y as a column vector. And if I were to perform addition divided by 2, so this is averaging between x and y's, I get my z value, which now fills the whole array, makes it into a 2D array that's filled out according to the equation z equals x plus y divided by 2. And then finally, I can go ahead and plot this out, and this now is showing x plus y divided by 2 instead of the earlier x times y. It looks slightly different. For example, like the first row and first columns are no longer flat black because this is incrementing. Another way to think about this is just diagonally increasing slope, two-dimensional plane that is increasing diagonally. That's what z equals x plus y can also be thought of representing. So with this in mind, you can actually go ahead and do something a bit more complicated. So we've already seen how you can use x as a row vector and y as a column vector and do computations with it to ultimately arrive at answers of 2D plots or 2D functions. You could keep on doing this. So basically, if I now want to go x, say, from some new value 0 to 11 and y from 0 to 11 and be able to create the whole grid, you can keep on doing the thing where you do NP range or lint space and then make sure to increase the dimension so that it's row and column. You can do that. Or there's also a convenience function called np.ix underscore, where if you pass in just two arrays, then it will correctly match the dimension and turn one of them into a raw vector and turn another one into column vector, such that you can just immediately start using it. So here, don't be too concerned here. What I'm basically doing is that now if I were to have an image that is 11 by 11 pixels, or function where I'm just trying values from 0 all the way to 10 for x and 0 all the way to 10 again for y, and if I'm treating the center to be something that's right in the middle, so it should be something like index 5, as the center, I'm just computing distance away from center. So here this is just Pythagorean theorem. I'm just computing the distance, and I'll be plotting the distance as a function of x and y. So all of that just means you'll get something that looks like this. Okay, so far so good. We'll actually come back to usage of something like this. So basically here, I haven't really covered how to exactly read out the value, but you can at least kind of get a sense that perhaps this means 0 because this is right at the center, and as you go further away, the distance should linearly increase, and it should look more or less circular. Now, one thing that actually automatically happens is that each of these grid points, or each of these pixel location corresponds to a sample from both x and y at which you're evaluating the function, and you're plotting it using some sort of color, right? So the color patch is one sample. And so if we were to show something like this, again, this is another similar function. Well, actually the same function we did earlier where I'm doing x plus y divided by 2. Each and every patch is just a sample at a specific location. So top left would be 0, 0. So x is 0, y equals 0, and z value ought to be 0 because I'm plotting the average between the two. At the very end, this goes all the way up to 4 and 4, so this value should be 4, and every other combination is shown by the function value, right? That's how it's mapped out here. Now you can achieve something that looks finer, right? Because this is actually pretty pixelated, for lack of better words, like that's by definition, this is pixel based. So it doesn't look high res. One way you can get around this is simply do it for many, many more samples. So here, instead of just using 5 points for my x and y's, I can use 100 points. So now I put way more samples between 0 and 1. And now if I generate a plot, now this is a 100 by 100 image that looks far smoother. Okay, so this is one way to achieve a smooth plot. But there's another trick. If you actually have something that is low res, like the 5 by 5 image, you can actually turn on something called interpolation, whereby you let the matplotlib, when it does the image plotting, try to guess the in-between values. So here, basically, I only provided function values for x and y's of 0, 1, 2, 3, and 4. And if you wanted to guess anything about in-betweens, it wouldn't do that. So it will always just do in terms of patches. But if you say interpolation, if you give interpolation an option, it will start making some sort of guess for values in between, making a smooth function. So all in all, what you get is that even though your underlying image is still 5 by 5 pixel, if you have, say, interpolation to something like bilinear, which means they will guess based on locally line-based assumption, where it connects the two dots and try to read out a line value in between any samples, you get something that looks pretty much as smooth as if you actually had far more number of samples, like 100 by 100. And in this case, you can even show that this is pretty much as good as the truth because this is a plane. So everything is linearly increasing. So if you try to guess in between values with a line, you get pretty much exactly what matches the truth. There'll be slight differences, especially towards corner, but does a very good job filling in. And it's definitely cheaper because you actually only computed 25 combination of values, right? You didn't go as much as 10,000 that you actually took to generate the real smooth values. But obviously this doesn't always work, because if it always worked, obviously this is the only thing people are going to do. They're always going to give you 5x5 image and just do a bilinear interpolation and go with it. The problem becomes when you have more complicated function that has a lot more ups and downs where simple linear guess is not that good. So for example, here I'm showing some sort of a sinusoidal modulation. So as you go from center out, based on distance, it goes ups and downs according to distance with the cosine. So this is without interpolation. Now I plot the exact same thing with interpolation. Okay, things look slightly smoother, but still not that impressive. And now if I use the 10 times as many points on x and y, resulting in 100 times as many points, you get like the truth. So you can see that there's a limitation to using interpolation. Bilinear is not going to always buy you to be as smooth as possible without breaking the truth. So here in this case, you still see the fact that this started off with a low-res image. You smoothen it out so it looks somewhat nicer, but it's nothing compared to if you were to actually use far more samples. So the more complicated your function is, the less likely the interpolation is going to actually do the trick to be able to fill in the gap, so to speak. All right, so we so far been actually talking about this, like showing us a function and reading off a value, and you kind of been intuitively following the fact that color must mean something. And in fact, a couple sessions ago, I mentioned the fact that there's a concept of color map. But let's actually try to make it a bit more concrete. So you can actually see what exactly each color means if you were to plot the color bar next to every image. So here I'm doing the same, another one, we're just doing x plus y as an image. And if you were to show this, this is the color bar you get. This is the image you get along with the color bar. And this time you see the color goes all the way from 0 to 2. And that's because 0 is the smallest value you found in the image, and 2 is the largest value you found in the image. So by default, it will scale the color to make sure it covers all the values it finds in the image. Now, of course, this default color plotting is not the only option. You can actually use any sort of other color mapping. So it's basically a choice of what a value means, or how a single value is represented in terms of what color is a choice you can make. And there are many pre-built ones that are provided for you. So most of the time, you'll probably just see selecting out of provided color maps. And for example, one of the ones that's very popular is gray. And it is the fact that oftentimes you think of these images that are 2D and only has one number that gets modulated across pixels as a grayscale image. And that's because typically you think in terms of just representing with the grayscale like this. So the value has some mapping to the color shade of the gray. It doesn't mean you're limited to this. You can actually use arbitrarily any other color map, and some better than other depending on what is it that you're trying to show. So here is another color map tool where it maps colors between purple and blue. It shows slightly better on my screen. So, or cyan. Cyan would be 0 here, and magenta is actually 2 here. And you can actually see a whole bunch of other color maps that are made available to you just by looking at the plt.cm sub packages. So I can actually, let me insert that above. So if I were to do here and say plt.cm, and if you do tab completion, it lists a whole bunch of color maps that is made available to you. So pretty much every one of these, aside from once in a while, it has a property that is actually not a color map. But most of these are color maps you can actually use. And if you actually were to install yet another package for that is meant to extend the capability of Matplotlib, one called, for example, Seaborn, there's a very popular extension package for Matplotlib. It gives you even more choices over color map. So here in this plot below, I just picked one randomly. So this is called Just Earth. And yeah, sure, it looks earthy enough, right? Now, and then here I actually gave you the link. So if you were to really go explore what are your options, say even just within the Matplotlib, this is a page you can jump to, and it shows you different options and some pretty colors. Now, we already mentioned the fact that when you were to plot with the imshow, it automatically scales, right? As in, it takes the minimum value maximum value of the image, and maps the color to go from the min to the max. So here, if I were to get, let's see, 0, what happens if image? Yeah, so actually I already kind of did this. So I already kind of showed this ahead, is that it's not limited to 0 to 1. Oftentimes in the past, I've been showing ones in which the color intensity goes only from 0 to 1. But in the previous examples, I'm already showing the case where it could go above 1. And what it would do is just scale it so that it will make sure that it can have the map that covers the entire range of values it sees in the image. That's the default behavior. So again, here if I were to do x plus y, where x and y goes above, then it would have changed. Here I'm actually even doing a slightly different one where x goes from -1 to 1, y goes -1 to 1. If I'm plotting x plus y, then the smallest value you find would be -2, largest value you find would be 2, and indeed that's what the color map actually tries to capture, the whole range of values inside your image. That's pretty nice. This is, most of the time you do want to see all the available values in your color, but it may not be exactly what you want. From time to time you might have an idea of what a number should mean in terms of color, like how exactly, what range should match in terms of the color map. So you can actually control this pretty easily. But to motivate this problem, let me actually just show you what if you didn't have this option. Like now, for example, I have a function, which is again x plus y. This again now goes from -2 to 2. So that's image 1. And in image 2, I multiplied this by 0.5, meaning that this now goes from -1 to 1 instead of -2 to 2. But if you plot them side by side, it will look identical because in both cases it simply mapped the color according to what it sees for that particular image. And this becomes even more apparent if you plot the color bar right next to it. So you see for the left image, the color maps from -2 to 2. On the right image, well, the smallest was -1 and largest is 1, so it only maps from -1 to 1. And superficially, they look identical to you. In order to tell the fact that 1 is actually smaller in range, you have to look at the color bar. And pictorially, it's not obvious. So this might not be exactly how you want to present your data. You might want to show the fact that the right-hand side actually is a squashed down version of the image that covers less range. So in situations like this is where you want to prescribe exactly what range is it that should be covered by the color map. And you do so by specifying 2 additional keyword arguments, vmin and vmax, standing for value minimum, value maximum for your color map. So here, with the knowledge that this is the smallest thing I ever find between the 2 images is -2, and largest being 2, I'm going to basically suggest to both images that vmin be -2, vmax to be 2. And now with that, you can actually visually appreciate the scale difference between the 2 images. The left one has much richer range, whereas the right one, reflecting the fact it is squashed down by 0.5, it covers less values or smaller range. And indeed, there's not as much difference across the image on the right side. So this way now, the color bars are matched up the same, and images itself reflects the difference between the 2 values. So something like this is something you want to consider whenever you're showing multiple images in your figures, right? Is that you want to make sure that you don't actually let it scale just per image. Oftentimes when someone looks at your figures, they actually assume the same color means something same. Just like when you're plotting 2 figures side by side, you try to make sure that the y-axis match up because you don't suddenly want something tall on left figure to actually be something exceedingly small on another figure, distorting the sense of how to compare the values. Same exact thing happens with the color map. You should be cognizant of the fact that if you're just plotting otherwise a grayscale image, if you do IM_show, it will automatically scale the color map. So unless you're careful about it, sometimes something that should look different can come out the same, or something that should look the same can come out differently if you forget to adjust for the color map. So something that you should always keep in mind when working with images, especially grayscale image, because you are in control of saying this color means this value. Okay, so that's enough with grayscale, right? I mean, grayscale so much, like we've been seeing color, but ultimately speaking, this was just one number per pixel, and there wasn't as much richness. So obviously, when you work with real data, you do encounter oftentimes working with actual colored images. After all, we live in the color world. So if you take a picture, most of the time you actually get a colored image. So obviously, you want to know how to work with it if that's something you have to work with, right? So for example, now I have a colored image that I took a picture on my phone and I want to do some analysis on it or just want to view it here. I have an option of loading it. And this doesn't obviously have to be about color image, but here I'm just showing how is it that you can load in an external file or external image into Python and specifically as a NumPy array. To do that, it turns out what you want is to use this another package. This is a new package I haven't covered yet called image.io. I mean, at least the name should suggest this is about the input and output of image. So it will give you functionalities for loading image and saving image. So here, you just import image.io just like any other time you want to use an external package. And here, inside the image.io exists a function called imRead for image read. And what you do is just pass the path. So here in this exercise or in this workshop notebook, I've provided you a sample image. Obviously, it's called image Japan, so it probably has something to do with Japan. And under the folder data. So if you just execute this, it should be able to find it and load the image. And obviously, if you just get the image, that in itself is not that interesting, so you want to see it. So you use the same imShow to show your image. And here is just a place I visited in Japan, like this year, sometime this year, I think. Or maybe it was last year. I don't actually remember anymore. Anyway, so it's a picture, right? It has full, at least some level of color. It's definitely not, black and white image. So it has color in it. And now I want to actually talk about how is it that you can actually represent color. So far we've only been talking about 2D images where per pixel you only have a single value. Obviously, single value wouldn't be quite enough to represent color. It actually takes more than that to describe color per pixel. So in fact, it's a bit enlightening if you look at the shape of what you just loaded. And you see it has fairly big height and width. The first two values are decently big. These are referring to the sizes of the image in pixel. But key is that this has 3 numbers in it, meaning this is a 3D array. And the last number is 3 to indicate this is a 3-channel image. So, okay, in case you're not familiar, right? Like I'm going to step through the idea. So when it comes to trying to represent colors, you have to specify 3 distinct values that corresponds to red, green, and blue, corresponding more or less to how human visual systems work, right? So by being able to specify those colors, you can actually cover pretty much all the full spectrum as humans perceive it. And any color that you see on screen is composed of specifying those 3 different mixtures of red, green, and blue. Hence, you basically have a red version of the image, green version of the image, and blue version of the image, or specific channels that together give you a full color image. So you can actually kind of see it, and the way you can kind of look into it is just by taking the image you loaded, and one at a time, well, you pick one channel and keep it the same, and basically turn off all the other channels to 0. And that's what I'm basically doing here. So first of all, I read the image again, call it red image, and just by using regular slice, remember this is nothing but a 3D array, so anything you've learned about slicing operation and assignment works just fine. So here I'm basically saying take all the height and width, so the rows and columns, but then index 1 into the channel, so that means the second channel, and make it all 0. And do the same for index 2, which is the third channel. This corresponds to the green and the blue channel. So effectively, I'm getting rid of all information present in the green and blue channel, leaving only modulations or changes in the red channel. So you should expect something to look quite red, right? So this is modulation in the red. This is the red component of the color image that you were seeing above. And what I do for the rest is the same exercise except for different channels. So now you see the green component, and then finally the blue component. And notice that I'm not just taking a grayscale image and changing whether it's in green or blue. These are actually distinct images, right? So if you were to look back to the original, something that looks more or less red, for example, maybe the flower petal color, it should be more or less higher in value when you actually look at here. And if there's not as much contribution of greens and blues there, it will just look dark there. So I'm just stressing the fact it's not like I just took a grayscale and make it colored in red or green or blue instead to make it suddenly look like 3 channels. These are distinct channel images that they all contribute different set of information that only when you put together you actually finally get the color image. So here, since I have 3 images that only contains information in red channel, green channel, blue channel, to recover my original, I actually can just add them all up. And if I plot it, I get the original image back. Okay, so hopefully that's pretty clear how red, green, blue channel works. So now you know how the composition works, like how you can go about defining and expressing colored images. This also means you can go ahead and create your own color image. So here I go through a bit of mathematical fun exercise, I guess, in which I just come up with different constitutions of, okay, what if I make the red channel this, green channel this, and blue channel this? So just see it. See here I'm saying I'm gonna modulate my red channel like this, where it increases in redness from left to right. And I'm going to control my green channel so that it becomes greener from top to bottom. And I'm going to control my blue channel so it becomes bluer from center out. Okay? I'm just showing how we modulate each channel. And of course, it's not color yet because these are just individually a single channel, or more or less grayscale image if you think it that way. Only when I combine them together, they now mean the redness, greenness, and blueness that actually finally expresses color. And this is precisely what I do. So see, each of these are actually plain 2D arrays. If you look at the way I derived there, I basically just create a 2D array, come up with, treat it a bit as a function, so it defines a 2D function. So they're 2D arrays, and now I'm trying to put them together into 3D array. So if you think about it, you're stacking these 2D images up, and the way you can do this in NumPy array is by using function called stack. So you just say np stack, and I stack my red, green, blue in that order. And I pass it as a list, and I say -1 to mean stack it in the last dimension. Remember, it's the dimension of a colored image is height, width, channels. So if I stack it up, I want to make sure the stacking occurs on the last dimension. If I stack in the first dimension, I will get a shape that looks something like 3 times width, height times width, which wouldn't register. If you were to give such an image to Matplotlib, they'll consider the first 2 to be the height and width, and last to be the channel, and it will be shocked to find there will be thousands of channels. So the order matters. So here I'm just stacking it up, and if I show it, this is what I get by mixing the red, green, and blue in the way I prescribed. So it's pretty straightforward to come up with however kind of colored images you like. You just have to come up with how the red changes, how the green changes, how the blue changes. And if you hit it just right, you can get somewhat pretty pictures like this. Okay, so one thing I actually want to take a bit of tangent here is in structuring the way you plot, right? So just to show my motivation, if you were to look here, you should notice there seems to be a lot of repeating block, or there are 3 repeats of what otherwise look very similar thing I'm doing. Obviously, they're not identical. I'm doing a plotting for the red channel, the plotting for green channel, and then plotting for blue channel. But I have a very, very similar structure between these 3 repeats in concept. I'm just doing differently. I'm just doing for different targets in terms of channel. But I always say the subplot to specify it's one subplot. And then I show the image. I make sure I turn the axis off. And then I also put a title. Now, there are enough differences, right? Title is different. What exactly you're showing is different. I mean, even the subplot position is different. So they're not identical repeats. So you cannot just say put a for loop and just repeat it 3 times. It wouldn't quite work. But it has something that's structurally very, very similar. So whenever you encounter something like this, and typically for me, the rule of thumb is if I'm seeing myself repeating conceptually same thing 3 times or more, I start to be intolerant about this. I cannot really tolerate the fact I seem to be repeating something 3 times, because I can easily imagine myself maybe going beyond this. I mean, 3 could be tolerable. I would definitely not tolerate if it's 10. It would drive me nuts if I had to do something similar 10 times. What if now I want to go and actually add another thing? Maybe for every single one of them, I actually want to add a color bar. Now I have to say plot.colorbar 3 times If I had 10 of them 10 times, that will certainly drive me nuts. So whenever you encounter this, let me say, to summarize, you do want to code it up. You want to think, how is it that you can express your behavior in a code? So for this one, I'm going to show you how I will approach it, and hopefully you see what the saving might be, and start to think in the future, whenever you approach something that seems to have a similar structure, maybe not just to this, but in your code, if you have something that's conceptually repeating, how you can save a bit of yourself time in the future by coding it up in more or less what we call scalable fashion. So here, what I'm doing is that, well, I created red, green, and blue channel images, so I'm going to put it in the list. I'm going to call it channels. And I know I want to put title along the line of their color, so I'm going to also put it in one called labels. It's a list. And I'm also creating tree axis using subplots. So remember, this is more of the object way of approaching matplotlib. I'm already telling matplotlib to create a figure object and create tree axis objects inside the figure and give me exactly the NumPy array that contains those tree axes, or lists, you can even think that way. The key here is that I want to visit these tree lists, one that contains the actual image itself, the channels, another one that contains the label I want to apply to the channels, and finally another one that's a list of axes to which I want to plot. Basically, every time I go out the first index on the one list, I also want to visit the same index position in the second list and the third list. Whenever you encounter situations like this where you have a couple lists, you want to visit same position in tandem or in triplets or together, this is where you want to use something called zip. So here what I've done is I do zip, and I pass in the tree lists I want to visit through. Axes, channels, and labels. And what it does is that it steps through same position index of the tree list one at a time. So basically, in the first iteration, it gives me the first position, so index 0 of axis, index 0 of channels, and index 0 of labels, returns it to me as a tuple. I'm already doing an expansion of the tuple to assign it into ax, channel, and label. And in the body of the for loop, I'm simply using that to do the plotting. So I do the image show on that axis. I give it the channel that I'm trying to work with. That's the image. I turn off the axis that I just code out on the axis. And I set the title on the axis. Remember that if you're doing object, it's not dot title, it's set title. So I'm setting the title on the axis object by using the label that matches for that particular combination I'm working through. All I know what you get is basically one for loop expressing these three things you want to do per channel, and you get the tree plots already showing. So as I said, 3 is somewhat of a magical number, at least for me. 2 really gets a bit to the point that if you start doing anything that you repeat twice and try to turn it into a structured for loop like this, you actually might be getting a diminishing return. You might actually waste time thinking how to structuralize this. Whereas like if it's 2 repeats, you're probably just faster off just doing it. 3 is usually indicative that you're probably going to do 4 at some point and go beyond it. So I at least urge you that every time you seem to be doing something similar 3 times, think how you can maybe generalize this so that it could work easily with 10. This was actually a theme of the homework assignment for those of you guys done, like where I asked you to ask for 3 numbers and do add, addition, and take the mean and take division. So with 3, whenever things like that, and I actually asked the question, can you do it for 5? Can you do it for 10? And the better thing, in my opinion, to do obviously was to write it such that it could work with arbitrary many number of inputs. Same thing applies here. Again, if it's only 2, probably you're fine just typing it, and you will see that's a theme through my notebook. But if it's 3 or more, I suggest that think whether a for loop or something like that can actually save yourself time. Okay, so here I'm just actually doing one more show of how the zip works. So here I basically have names, colors, and ages of 3 dogs. So a position match, right? So Moku is the first dog that is black in color and is age 7. Chabo is the second dog with brown in color and age 6. And finally Lulu is the third dog with the gray in color and has an age 1. And I want to visit them together. So if I want to visit the index 1 of the name, I want to visit the index 1 of the color, index 1 of the age. And again, that's where zip is for. And I can get something like this very quickly. It's a very handy one. It could also be very much of a brain messer if you don't think about it sometimes. There are many, many fancy ways of using zip as well. But at least for this very, very basic usage of it, it should be fairly straightforward, hopefully. And hopefully you can start to see the benefit of using this instead of maybe like just plain indexing. All right, and at this point, I do also want to cover a topic that I haven't really covered much in terms of NumPy array, because it oftentimes doesn't matter as much, but it's a good thing to know, especially in the context of image, is something about data types. So just like we talk about types of variables and types of literal data in Python, there are like integers, floats, strings, and booleans. The NumPy array also does have a data type I alluded to some time ago. You could actually have floats expressed or booleans expressed in it. And it could also be an integer NumPy array. Most of the time you don't really care too much. Like most of the time you're going to end up finding your NumPy array becoming a floating point NumPy array because that's the most flexible. But when it comes to images, whether it's int or float actually does matter. And the reason is because when something like matplotlib's ImShow tries to understand a 3D array as a colored image, it expects certain things about the array. One is that if it's an integer, if the data type of array is integer, it expects any one value in there to be between 0 and 255. 0 being the lowest, the darkest, and 255 being the highest. Any value that's below 0 is pretty much considered the same as 0 when plotting. Anything above 255 is considered as the same as 255. So those are called saturation values, right? Whereas now if your data type is float, it suddenly changes to say 0 is still 0, but 1 is the maximum. So this is where you have to be careful. Like if your data type is float, your range ought to be between 0 and 1. So if you just take something that was integer, expressed between 0 and 255, and suddenly convert it into float, vast majority of the values are already saturated. You have to actually make sure you scale it down. We're not going to encounter much of it today, but in the next session, that is actually almost a week from today, when we cover the neural network, something like this actually becomes relevant and comes up all the time. This conversion between 255 to 1 or back to from 1 to 255 does come up all the time when working with images. So anyway, just to illustrate, the one that you loaded from the file, the JPEG, actually, again, is a colored image. And if you look at the max and minimum value, it is 255 and 0. And indeed, the data type is uint8. So this is not straightforward integer as you might come to expect, but it really just means that this is an 8-bit integer that's unsigned. That's a bit of mouthful and it's a bit of a jargon. All it means is that it expresses numbers between 0 and 255. It's a limited range integer. Whereas the ones you created with the functions, because by default if you create a NumPy array, it's a floating point NumPy array, what it came out was actually a float image, so things like that we saw. If you look at the minimum and maximum, I actually was careful in construction that it doesn't go above 1. And data type is indeed float. So the question is, of course, like if you were to say multiply this whole thing by 2 such that the maximum now is 2, what will happen if I try to plot it? So it's hard to appreciate what exactly has happened, but it actually has just basically clipped it off. Anything that went above in intensity was clipped off, and at least Matplotlib has been nice enough to tell you, hey, this is actually exceeding the expected range. So what you're seeing is not a good reflection of what it ought to be if it was a valid image the Matplotlib would otherwise expect. So it says it ought to be 0 to 1 for floats or 0 to 255 for integers. All right, so that was quite a bit we already talked about, just trying to understand image itself, right? So we already covered how image and grayscale is expressed, or another way to think is, in reality, if you have any 2D array information, you can almost think of it as an image. And I do want to stress the fact that this comes up actually all the time, and it's a very good trick to know. If you have a 2D array, aka matrices in many contexts, you could just look at it as an image. So if you have a 2D array that you're wondering about structure, and if it's anything, say, bigger than like 5 by 5 or maybe upwards of 10 by 10, you are far better in terms of being able to understand it if you were to plot it as an image rather than just looking at the sheer matrix itself. Like 100 values to appreciate by number is usually too much. It's definitely above my memory capacity. So whenever I encounter matrix like that, I'll just go ahead and plot it, and you get some visual appreciation of what it looks like. Of course, one stressing point is that whenever you do that, you have to make sure you understand the color map you're using. If you don't use the right color map, or if you don't control the range of the color map, you can get a very distorted view of your data. Just in the case, like if I were to scale it down, if I let the image show just do its thing, it would just auto-scale. So the scaling doesn't seem to affect the result at all. Like image will consistently look the same if I multiply by 10, 0.1, 0.001, 10,000. It will constantly look the same. And unless you're careful, you might get confused, or you might think that maybe nothing has happened and just proceed. Obviously, what you want to do is you want to control the Vmin and Vmax to get a sense of what does the color actually mean. This is also, more or less a statement to say that if you have a color plot, you really should have a color bar that goes along with it. A colored image that's supposed to be representing actual values that doesn't have a corresponding color bar is as useless as it can be, right? Because you don't really know what the redness means. It's actually really up to whoever plotted it. Like you might think that it just nicely, smoothly goes, but who knows, it might be using logarithmic scale or whatever other scale they appreciate. Color bar lets you actually see what is the actual correspondence between the color and the value that's getting plotted. So you expect that to others, and you should definitely expect that to yourself whenever you're generating these plots. Okay, and then we look at how different ways you can express color and how you can think of as 2D functions. So all in all good, but if you really think about it, we hadn't really done manipulations and processing on image, which is the next topic. Okay, so when I say manipulation and processing, I just really mean if you were to take an image and do something with that, knowing it's an image. And it could start as simple as just working with an image and treating it as a NumPy array and do some computations on it. And because the 2D NumPy array or 3D NumPy array is an image, any modifications you make on it is effectively image manipulation or image modification or even processing depending on what the complexity that's involved. So just keep in mind that whenever someone says I'm processing image, it's more or less just a statement saying I'm working with the 2D array or 3D array data, and oftentimes just respecting the fact this is an image. We already saw the fact that if it's a colored image, you should try to respect the fact that it shouldn't go values beyond 0 to 255 if it's an integer, or 0 to 1 if it's a float. So any operation that gets you out of the regime effectively makes it an invalid image, unless, of course, you do something before you actually plot it to make sure it becomes a valid image again. All right, well, so that's a lot of basis, but we could just start with this. So here, from a couple examples from now on, I'm just going to use a face image that comes with SciPy Miscellaneous package. If you guys remember, this is the face of a raccoon. So you get to see this a lot. Actually, for whatever reason, this has now become the standard for the SciPy packages, this default image. It used to be something else. It used to be a picture of a particular woman that actually has been very, very popular in the field of computer vision for quite a few decades. If you're interested, if you search for something like Lena computer vision, it will show up good 30, 40 years of history. At some point, finally some people came along and thought okay, that doesn't really seem appropriate. And if you look it up, you understand why this is a bit inappropriate perhaps. And it has been changed, and SciPy decided to adapt a very non-offending picture of a raccoon, because I guess no one gets offended by this, or there's no problem with this per se. And maybe they got permission of the raccoon as well. All right, so the first point in terms of manipulation is just treating as a NumPy array. Anything you do thinking as a NumPy array is an image manipulation. Again, as long as you don't really break the rules of what an image should be, right? So, for example, cropping an image. So, if you might, just to define it, cropping an image, you take an image and you just shrink it down to a certain size, and you're not scaling it. You're just cutting down some edges. That's cropping. If you really think about it, that's nothing but slicing. So you can achieve cropping of an image. So here it's 768 by 1024. Oh yeah, just to highlight, it is height times width because it's rows times columns. So it's height times width, it's not width times height. So here it's 768 pixels high, 1024 pixels wide image. I can crop it. I can crop it by say 200 pixels off of each edge. And I can do that just by doing slicing, saying I'm going to go the first axis. This is basically cropping along the rows or height dimension. Starting at 200 point, and going up to minus 200, meaning it's a 200 from the end. So effectively, I'm cutting away first 200 pixels and last 200 pixels, throwing away 400 pixels in total on the height. And I do the same on the second axis. I'm throwing away 200 on each edge. Net effect being that I kind of have this more zoomed in view because I just cut away the corners. So cropping is as easily done just by slicing an array. And this actually works just fine for color as well. Just to make sure when you crop it, you pass in the third column is colon to say select everything. Or in fact, since you're just working with the first two axes and not touching the third axis, if it was a colored image, if you just still use the exact code I provided here, it will happily preserve all the channels, meaning that it will achieve same exact cropping we have performed here. Okay, so that's cool. Another one is, say, flipping. So we've already seen how you can reverse a list if you were to use the slicing trick. Instead of like providing any starting and end, you just provide the last number, which is a step. If a step is negative, then it actually counts backwards. So if I provide a slice of colon, colon, -1, I will flip that axis. So I can flip an image, say, horizontally just by passing the colon, colon, -1 to the second axis, right? Because it's the height and the width. I want to flip it horizontally, so I pass it to the axis index 1, which is the second axis. And I have it sideways flipped. And of course, I can do up-down flip or vertical flip by passing in this colon, colon, -1, the reversal to the first axis or index 0, because that's the height dimension. And I get it to flip it upside down. So you can see that oftentimes things that you may not associate in terms of array manipulations can easily translate into fairly meaningful behavior in image. So another thing is you've already seen how you can take slices and assign new values in it. Well, this is exactly how you can manipulate images as well. I can take image. So here I just refetch the image. And actually, even I'm being very cautious here. I make a copy of it because I know I'm about to change the image. So I make a copy. I call it image_c to indicate this is a copy. I basically get the height and width by looking at the shape. So remember, if you do dot shape, it returns the shape in tuple. So if I assign it to the left-hand side to the number of variables that matches in length, each of them gets the size in the specific dimension. So it's height times width. So if I say h, w equals image.shape, the height h becomes the height, w becomes the width. So here, basically all I wanted to do is I wanted to make to the right side, the right half of the image gray. That's what I'm trying to achieve here. The way you do that is by slicing onto the second axis, right? Because the first axis, again, is the height. I'm going to keep on saying that for a while. And the second axis is the width. So since you want to do the right half, you're going to take the second axis and start at the midway point and slice beyond it. So the midway point would be something I can compute by saying w//2. Remember, // is an integer division because the position has to be an integer. So I'm doing the //2 to get roughly the closest half point because it may not be exactly the half depending on how many pixels you have. So roughly the closest to half point, and then I just slice beyond it. And not only that, I assign value 127 in it. Now this means that this image is actually 0 to 255. With 0 being the lowest, 255 being the highest, 127 is the midway value. So in the sense of the grayscale, this is the gray, like the mid-range gray color. So basically, all in all, what you get is the right half of the image is now blocked out with gray, because that's exactly what I just done. Okay, so hopefully this whole operation makes sense. So you can do any sort of manipulations that you can think of in doing NumPy array in context of images. It's really no different. This is just yet another NumPy array. It's just that it has some visual meanings or something you can visually appreciate. So any operations you perform translate into some visual image manipulation. I'm pretty sure I meant masking of an image. So let me actually fix that. Masking of an image. Okay, so you can actually achieve something even more interesting if you combine multiple arrays together. So what I do here is that let me just create an image that is same exact size as the image that we're working with for raccoon. And I do that just by getting the shape and passing into the convenience function np0s. Remember, this creates an array filled with zeros of whatever shape you specify. So I create a variable called mask, which is a 2D array, same shape as the image, but entirely filled with zeros. If I were to look at it, of course it's entirely black. It's 0, right? Now, if I were to take this mask and multiply onto my image, and now I plot it, well, knowing the fact the mask is entirely 0, if I multiply onto my image, what do I get? 0, right? It's entirely 0, so you should expect no different than seeing yet another entirely black image. So you might be wondering, what's any good of this? Like, why is this at all interesting? Well, so far it hasn't been, but it becomes interesting if you make some of these values of the mask non-zero. So here I'm actually basically saying I want to take some mid-range, so I'm basically taking some edge away from the edges away, so I'm just taking some center rectangular area of my mask, which is now currently entirely 0. But within the center rectangle, I want to assign value 1 to it. And then I show the value. I show it as an image. Effectively, basically get something like this. Now, there's a black rim, and the center is white because it's 1. And notice that this is 1 because this is showing white because it automatically scaled, right? I'm using gray color map. If I show what just I am show, it auto scales to make sure it ranges from 0 to 1, 1 being the highest, so it shows up as a white. But here I do want white to be 1. I do want the 1s. Now if I actually take my image and multiply with my mask, which is 1 in the center rectangle and 0 everywhere, what it effectively does is that it cuts away the corners and keeps the center. So this is the telltale masking that you can perform on an image just by having an array that is filled with zeros or ones, where 1 would be where it effectively becomes transparent in some sense. If you were to multiply it, that will keep the image as is, and anywhere that's 0, it will block that image out. Okay, so that's pretty interesting, but you can actually do even more, even fancier masking if you could work with x and y values and define a 2D function and also combine with the Boolean array. So here, this is actually the same kind of code I've written earlier where I just have a image. Again, same shape as the image that we're working with. So notice that I get the height and width from the image. But I created this one, and what this is a computing distance away from the center of the image. So again, if we were to plot it, it looks something like this. So we've already seen this earlier. But now if I actually were to crop this, or if I were to do a Boolean filtering on this, saying that since each of these pixels is telling like what is the distance away from center at that pixel position, I'm interested now to say I only want pixels who are within certain distance from the center. And I can do that just by taking this image, which I've been calling R for radial distance. If I say, okay, I want this radial distance to be less than 300. So if you were to look based on color bar, that's roughly where blue transitions to green. So I'm talking about this radius. So here I'm basically saying mask is R less than 300. And if you recall what this does, this is a comparison operation on NumPy array, which should return you a Boolean array. So this is an array filled with trues and falses. I don't think I've stepped too much into this point, but if you actually work with Boolean array and start doing math on it, assuming that you can do math on it, it will automatically basically fill trues and replace it or like consider it as ones and falses as zeros. So oftentimes you can just go ahead, use it, and treat it as if it is actually consisting of zeros and ones. And here basically I'm doing the same thing here. I'm just plotting a mask, which is actually a Boolean array. But when I try to plot it, it will understand that I don't necessarily want to see a grid filled with a bunch of trues and falses as words, but it wants to see true as ones, false as zeros, so you get something that looks just like this. So again, white part is the 1, which corresponds to true. And I get here, again, by taking my image, which is really more interpretable as 2D function that computes distance away from the center in the image. And I just show a particular point at which I want to cut it off. I basically want to say anything that has a radius less than 300, that should be true. Anything beyond should be false. And with that, I successfully get something that looks like this. Looks like a circular mask, where center is 1 and outside is 0. Well, if I have a mask, I mean, you probably already guessed what I'm going to do. I'm just going to apply on my image by multiplication, and now I have circularly cropped image of a raccoon that you can happily use for something like Twitter. Right? Because that's all what the Twitter does and Facebook does nowadays is the circular cropping. So effectively, if you want to do image manipulation yourself to do circular cropping, this is exactly what you would do. You need a mask that you can apply on an image. And when I say that, I'm of course half joking, but not really. This is exactly how numerically some operations like cropping occurs on computer. There's really no more magic to it. And I'm not necessarily making anything more complicated than it has to be. This is the operation that gets performed to achieve something like this, where you change what gets shown. Okay? All right, so along the line of this cropping actually comes some idea of thresholding. So thresholding is exceedingly common operation you perform image. And effectively, idea is that you take an image, and especially for the grayscale image, this particularly applies, but you can extend this to colored image. But for a grayscale image where each pixel has an intensity or value in it, you can basically say, I want all the values that is either above or below the threshold, where above or below being determined by which one you want. I'm not necessarily saying like I want all the values that's either above or below, because that'll give you back everything. Or maybe it would just give you back everything but exactly equal to. And what I mean is that you want to maybe sometimes just look at all the pixel that has certain values of intensity or higher. So you're thresholding it. So here I'm basically taking my raccoon image, and I just arbitrarily came up with this number 170 to say, okay, I want to see the raccoon image, the part of raccoon image that is above 170. So that gives you this. Interestingly enough, if you threshold it, you still kind of get the sense that this is a raccoon, because it's effectively still getting the highlighted portion of the raccoon where it has a high brightness and just picks it up. And this is how, for example, you can get an image like that of the famous image like of Obama, where it just thresholded and make it into two-tone color. I mean, this is exactly the operation you perform. If you have any fancy software like Photoshop, where it actually just does this two-tone changes of otherwise grayscale image or even color image, this is what they do. They just threshold. Okay? So now you got basically this highly stylistic thresholded version of the raccoon. Well, this is, again, like just a Boolean if you think about it. I just ask what's greater. It's giving me truths and falses. And it's just treating us ones and zeros for truths and falses, respectively. And you can think, whenever I have something that is filled with ones and zeros, I could use it as a mask. I could just multiply this onto original image. Now, you just have to think what that would mean. Right? If I were to take this and multiply into original image, what is it that I'm actually doing? Well, what I'm basically doing is that I'm picking out a pixel position that is at least 170 intensity. So I'm picking relatively high intensity pixels, and I'm going to just show it true. I'm going to show that part of the image and let it show the actual value it has. But anything that was lower than that is now flattened out to be 0. So it's actually more of an operation of thresholding things away. Anything that was below 170 is flattened forcibly to be black. And you see that if you multiply the thresholded image onto image to get your mask image, and if you plot it, indeed, the part that wasn't bright enough now is completely black. And this operation of thresholding happens a lot. And I will have an example that is closer to real life in the sense of like biological science examples. But if you were to have an image of, say, cells or maybe colonies in the petri dish, and you actually just want to capture the part that has some value in it, some intensities, or maybe this is a gel after electrophoresis, you're trying to just catch the part that actually has radiolucence. In that case, you don't care about all the backgrounds. The part that would otherwise look more or less dark, but because of the imaging system, nothing is completely dark just because you don't like those values. Right? Imaging system will try to capture as much as possible, so even the ones that you don't quite care for often have some values that's not equal to 0. But since you don't care for it, you often establish a threshold and just remove everything, or at least flatten them out all the way down to 0, so that it doesn't actually bother you and allow you or whoever you're trying to present the data to focus on the part that matters. We'll come back to this idea. All right, then, okay, I'm also just saying, like, well, in the past when we talk about Boolean array, we kept on using for fancy indexing. Remember the fancy indexing where you can use Boolean to select out specifically those values? Well, of course you can use it. Just because you're using images doesn't mean that you have to use it as a mask. So here I basically take the exact same places, so those pixels that were higher than 170. And this time, instead of using it as a mask, I'm using it as a fancy Boolean indexing. And now you're going to take all those values and set it to 0. And now, if again, like the key to these things is always think about what the effect would be before you see the result. Well, if you think about it, I basically take high pixel intensities and make it 0. So overall, you should be now losing high intensity positions. And that's what you get. The high intensity portions now are brought down to 0. And you can see it actually starts to lose the information about the image. You can still make out it's raccoon probably, but it's definitely harder. And this is at least an interesting, and at least anecdotally interesting, to suggest that those high intensity color pixels were actually very informative about what you're seeing. Things like that, thinking about what are the parts of the image that really gives you the information that matters, is actually something that becomes key core component whenever you study topics of machine learning and image processing and image analysis along the lines of, say, image recognition, object detection, segmentation. Stuff we will briefly touch upon next session. All right, so another big topic that I'm going to tell you ahead that I'm not going to do justice to. One, because there's too much to be discussed about this. And one is that I cannot really discuss this in quite detail without really diving into the concept of what a filtering means, what is the frequency constitution of an image, how you conceive a filter as like Fourier domain analysis, all these jargons that will naturally come whenever you look into filtering. They're not there just to scare you off. They are there because if you truly understand it, it helps you understand and design filters. That being said, you don't really have to know those mathematical details to at least appreciate the net effect. And that's what I'm going to try to focus on here when I talk about filtering of the images. If filtering of the images, or not just this topic of filtering in general that comes again and again when you work with signals to systems, signal processing, image analysis, or even actually neuronal signal processing, say even in the context of EEG, EEG, ECOG data, or fMRI, the idea of frequency information matters, and the filtering goes very much hand in hand with that topic. If that's something that you guys are really interested in, that's a discussion topic for entirely a separate workshop. Okay? So with that whole lengthy excuse of why I'm not covering the details of the filtering, let's at least look how the filtering achieves some interesting effects on the images. So whenever you're doing processing on images, you tend to think about taking an image and let it run through some process that modifies or may potentially enhances some features of the image or removes some unwanted features of the images. Typical example includes you have an image that is very noisy. If you do any photography, you know that if you go with high ISO, it lets you take images in darkness, but you actually get a lot of this like speckle noises because it's now picking random photon hits on your image, so you get very noisy image. Whenever you encounter things like that, one way that you might imagine of making it look nicer is to just blur it out. So there's some idea of like maybe blurring operation you want to perform, and that's typically thought in terms of blurring filter applied to your image. Or maybe you want to do the other way around. Your image is way too blurry, or overall it's just low in contrast. You can actually apply a filter that enhances contrast by looking locally nearby pixels and adjusting your image. So a lot of image processing are done in terms of filters. So when you want to work with these, there are ways by which you can just use plain NumPy array and operations that we haven't really talked about, such as convolution, to work and implement your own filters. Or you can just simply take something like SciPy's ND image for n-dimensional image subpackage and use function that's provided by it to already get what you're interested in. So first example we're going to look at is the Gaussian blur filter. So this is if you want to blur your image out, or if you want to smoothen out your image, maybe because it has some noise in it, or maybe just you just want to like not really show every exact detail about your image. Whatever your motivation is, this lets you achieve it by using a blurring filter. And a very typical example of blur filter is what's known as a Gaussian filter. One intuition, at least I can give you without really talking in terms of convolution or any of those math involved there, is that you can make something smoother if each pixel gets replaced by a local average. Basically, if you look at any one pixel value, it might have like sudden jump. Maybe that one pixel is suddenly white and everyone else around is pretty much one tone of gray. The way by which you can achieve smoothness, if you think about smoothness, means that nothing changes that dramatically. Nearby pixel has similar color. You can achieve it by basically replacing this suddenly white pixel by an average of the nearby pixels. So it still has a bit of higher value because you're considering yourself as part of an average, but because you also consider your neighborhood, you kind of become a bit toned down. Just like if you're working in a group of people and you're kind of the extreme person, everyone else is not that extreme, overall you'd probably be a bit less extreme of a person, or conclusion might be less extreme. Same exact thing occurs in the context of Gaussian filter. So this local averaging is the key when it comes to smoothing, and it's called Gaussian filter because the profile by which it weights nearby pixel is Gaussian or normal distribution, where you weight yourself the highest, your next neighborhood next high, but as the distance goes on, you start to listen less to them. So all in all, let's just see an example of it. Again, I'm taking the image of the raccoon in gray, and here I'm actually blurring it by taking a Gaussian, in the image Gaussian filter. The way it works is you take that function, you pass in the image you want to blur, and you also pass in this keyword argument called sigma, which stands for standard deviation of the Gaussian or the normal distribution, which effectively controls how wide the filter is, which in effect controls how far away are you going to listen to. If you really listen to a lot of people's opinion, you really become very milder of a person. Same thing goes on with pixel. If you really listen out for far away distance, you're really going to have a very much of a smoothened image. So here I'm trying two versions. I'm filtering the same image, one with sigma equals 3 and one is sigma equals 10, with the expectation that should be that higher the sigma, the blurrier it becomes. Okay, so here, again, this is where I kind of struck my magic number. I wanted to show the original, the first blur, and the second blur. There are 3 images. I didn't want to write plt.imshow 3 times. That would drive me nuts. So I basically put them in a list. I also went ahead and put create another list called sigmas, because I'll be using that to indicate what was the sigma used for each of these images. Here I'm making this implicit assumption / statement that if sigma equals 0, that's my way of saying there was no filtering that went on. So all in all, if I plot it, this is what I get. So sigma equals 0, again, is original unfiltered image, or technically equivalent to filtering with sigma equals a Gaussian filter with sigma equals 0, meaning it's not really filtering. Filter with the sigma equals 3 makes it slightly blurry, and you definitely see the fact it gets much blurrier by the time you get to use sigma equals 10. So hopefully you see how the Gaussian blur could be used to just blur out your image. So opposite operation of, at least intuitively opposite operation of blurring is sharpening. Sharpening means that you actually highlight the difference in neighborhood pixels. If basically pixel value changed from say 0 to 100, you want to highlight the fact by actually making the difference even bigger. That's what sharpening is going to do. This is, if you think about it, quite the opposite of what blurring would do. They will try to make neighboring pixels as similar, somewhat more closer, but sharpening will make them further apart. And net effect is that edge stands out better. And sometimes this gives you a sense of higher fidelity or higher image quality. Don't be fooled though. Like if you start with an image and no matter whatever you apply on it, you can never ever increase information in it technically. You can only have as much information as what started out with your image. Anything that makes you think that this got better is really perceptual. It's doing things to make you think this looks better, but not necessarily telling you or giving you actually more information content. This is something that is subtle, And if it's more for aesthetics or artistic purposes, no one really cares. But if it's in terms of using image to convey information, don't ever think that you can actually somehow filter an image to get more information out of it. That would never, ever happen. All right, so that being said, I almost sounded like I'm very negative towards sharpening. I'm not. All I'm just trying to say is that sharpening has its own purposes. Most of the time it's aesthetic, sometimes to highlight what you want to show, but don't ever think that it suddenly made a crisper of image. Here, what I've done is I take the original image, again it's a raccoon, I blur it. We've already seen how the blurring works. And what's interesting, the way you achieve sharpening is you take an image, blur it, and subtract the blur away. I'm not really going to go into why that really achieves it. One way to think about it is that anything that otherwise would have been present overall, so that's something that's smoothened version, you just take it away. That effectively highlights what is actually not smooth about your image. So here what it's actually doing is that it tries to do sharpening on the blurred image. So it takes the original, blurs it, which makes it lose information for sure. It looks blurrier. And now it applies this blurring on the blurred image. That's how you get the filter blurred image. And you subtract a bit of the filter blurred image away from the blurred image in its attempt to make it look sharper. Maybe make it look closer to the original. Okay, so this is literally where picture is worth 1,000 words. I can just show you the net effect, and this is what you get. The left is the original. The center is the blurred. You can appreciate the fact it is indeed blurrier compared to the original. And the right is where I start with the blurred image and apply sharpening on it. And you could argue that it almost looks as good as the original. Right? Basically, but it didn't cheat in any way. It didn't suddenly like go to the original and grab the information that was lost between going from original to blur. It really did only work off of the blur. So by doing some trick, well, what do you call a trick is obviously always going to be a bit of like question of argument, but here at least you're taking the blurred image and do manipulations on it to give you a visual impression that you actually recover some details. Okay? But I'm stressing this is not information recovery. Anything that you actually lost from original to blur is forever lost. And if you went from blur to resharpen, you definitely did not increase information. In fact, you most likely even further lost more information. But it's really in the sense of just how you lose information is not necessarily always correlated with how we perceive an image to look. As in, like, we don't necessarily think of image to be worse in quality just because they lost information. You can actually lose information in such a way that it makes it look nicer and crispier of an image. But there are actually many details here that simply lost from compared to original. All right.
So would you look at sharpening if you just sharpened it from the original?
So if you did it on original, it will look sharper than original. It's just like because the original is as high fidelity as you stand for. If you start with something that look already decently sharp and sharpen it, then you start to see what looks like an artifact. Basically, things look a bit too edgy. I mean, you can even actually try applying on it. So I can actually quickly do it, right? So if you want to do it, all you have to do is basically replace the blurred image with image instead. So I'm just going to give you a minute to think why that would achieve what I'm trying to do. So this way, image is going to be image, blurred is still going to be the same image, and the sharpening is now applied on the blurred. If you did that, this is now what you get. And you can definitely tell, okay, this is not making any sharper per se. This is not looking any better. So you might be shocked to see the fact that going from original and sharpening gives you this crappy image. But somehow if you blur it and apply sharpening on it, it looks somewhat nice, right? It just, that's the effect of what this tries to achieve. It's that it really highlights a sharp, like what could be sharper. But because original was as high definition as it could be, any additional attempt of sharpening this like sudden changes, now it's effectively catching onto noise. That's what's happening. Basically, if you apply sharpening on something that is not blurred, you will actually highlight the noise, things that you don't really care about image. And this is actually one thing that's fun of the image processing and filtering. Obviously, I said I'm not going to go into it, but something that's really fun in my opinion is that there are arguments you can make of why it's actually better to do blurring followed by sharpening if you want to say achieve two things. Not try to lose too much information, but get rid of stuff that you don't want. For example, noise. Blurring tends to get rid of noise. Let me just put it back. Blurring tends to get rid of this noise because of local averaging. It makes sure that no one is suddenly changing a pixel value, which is usually indicative of the fact that it is a noise. So blurring gets rid of it. But in effect, in the process of getting rid of the noise, it tends to also get rid of features that you actually would have cared for. Some nice changes in the way the fur looks, all these high definition details. Sharpening then tries as much as possible to highlight that portion, because it's not so much those changes are really completely lost, it's just now harder to see, and sharpening just tries to highlight that fact. So if you think about sharpening, it just really goes for something that changes a lot. Like some sudden changes in pixel is what sharpening tries to catch on to. And if you apply on original image, the thing that changes the most about original image is actually noise. That's why if you do sharpening on original, you get very noisy image. But if you do it after blurring, blurring does somewhat get rid of the noise. So now if you try to catch on something that changes a lot, that tends to be actually part of the original image, the feature of original image that you do care to see, hence it could look a bit nicer. So it is actually not uncommon, for example, in photography that you take an image, you do blur it first, and then you resharpen it. This procedure is fairly common, and oftentimes it's even like one button away, or you might actually just do it automatically depending on your camera, because they know that that combination together can actually achieve the best of both worlds. Get rid of noise, but without losing picture quality that people tend to appreciate. Okay, so obviously this is something that can go on, and I can talk all about different filters and such, but I'll kind of leave it for here. All right, so another very popular topic when it comes to image processing, and I believe this is the last chunk. Yeah, this is the last chunk. So it actually would be fairly early because I did want to talk a bit about the next session, is this idea of foreground-background separation. So what I mean by that, when you have an image, so even in the case of raccoon, you can perceive of some of these things in the image to be the foreground, meaning a particular aspects of an image that you care to identify. For example, the raccoon itself. So you can argue and say the raccoon itself should be the foreground, and anything else is really the background image, right? And this might be actually particularly more obvious if I, for example, like instead of the uncolored version, I get the color version, and I just show you the image. Here it's even more obvious how you could go about separating the foreground and background. Like backgrounds are all in this green and maybe a bit of blackness. So that's the background information. You quite couldn't really care for the fact that he was in like what looks like green grass, right? You don't really care about that. You are trying to maybe look at the raccoon. Of course, unless people took this image out and saying this is a sample of this particular species of plants and this is a terrible choice of an image. But most likely this is an image of a raccoon. That's your foreground. And the background is this green stuff that you don't care about. So this idea of like when you're trying to process an image like this, you often do want to preserve the foreground and get rid of the background, or maybe at least be able to separate them out. Maybe you don't necessarily want to get rid of the background. Maybe it has some information you could use. Maybe like you can guess where this raccoon was to be found. But it's still a separate set of information. At least it's perceived to be that case in many, many image processing applications. So this foreground background keeps on coming up, and this will come up again and again if you work on topics like object detection, object recognition, and there's the difference between the two, and image segmentation. These are all different. They sound similar, but they're all different subtopics of image processing. And in case you have never heard of it, this is also one of the prime topics for machine learning and neural network nowadays. This is where neural networks is the leading architecture in machine learning that has been excelling at. And not like it's been excelling at actually past decade, this is actually news over past 6 years or so. 6 years ago or so, it wasn't doing that well. But then there's something happened, and now we have machine learning algorithms implemented as neural networks that actually can far exceed human performance on some specific topics. And oftentimes that specific topic is about images. The image recognition, image processing, image-based machine learning task is where machine is the most advanced in. Probably next up in research topic would be something along the line of natural language processing. Nowadays, we're not too shocked to find that your phone comes with some sort of personal assistant you can talk to. You can actually talk, and they most of the time understand you. Maybe it's not perfect, but it's definitely doing far better job than what you could have imagined, or at least what I could have imagined mere 5, 6, 7 years ago. It's doing far better, and that's also thanks to similar kind of architectural and machine learning change that's been applied to it. And there, obviously, the topic goes on and on. But again, just to bring it back, image is the favorite topic. It often is what people do still work on in coming up with the next architecture, next innovation, machine learning. And if this is something that interests you, then I think that you'll be happy to find it. Next session, we're going to actually at least get a taste of it. We're going to try to implement our own neural network. Nothing super fancy, but at least something that actually can train within a session to actually do decent job classifying numbers. You can actually show an image of a number, and it can tell you whether it's 1, 2, 3, 4, 5, or what to 0 actually. It will do a decent job on it, and you can already implement it with Python. So that's kind of the background I did want to give you, and why this image is an interesting topic to go, even if the interest was just for the merely on the sake of doing machine learning. Okay, so enough said about this. Let's actually look a bit more about not so much neural network approach of image processing. So here's an image I prepared for you, which I'm telling you something like this is like on your petri dish, you just got a bacterial colony, right? I mean, it will look like this, right? It looks a bit blurry. Maybe that's just the quality of the image prompt. It also a bit of slight amount of noise in it. But the idea is like, okay, if you're given something like this, you do want to do something like a foreground-background separation. Here it looks pretty straightforward, right? The background is pretty pitch dark, and the foreground is this very white thing in front. But at least, if you cannot do foreground-background separation on this, then you likely wouldn't be able to do any other foreground-background separation. This is a good starting point. As much as I say it's a starting point, this is as much as we're going to cover for this session. But at least you can kind of extrapolate what it will look like if you were to work further on to this prompt on much more difficult prompts. Now, this particular image, because I loaded from JPEG, has 3 channels, meaning this is actually a colored image, whether you believe it or not. Yeah, and it's just a colored image that's black and white. You can totally do that, right? Black and white is actually a valid color. So, and you can see by the fact that am I showing it? No. If you can see by the fact, if you do image.shape, indeed it has 3 axes, so it's a 3D array. And the last axis is indeed 3 to indicate this is RGB, or red, green, and blue image. And because the color doesn't matter so much, this actually only contains grayscale values in it. You can go ahead and simplify this by collapsing across the color. This is some fairly common operation you do in a lot of image processing. Like you take a picture of something, almost by default, just by the design, they will come with RGB. But oftentimes you don't really care. Just say it happens for like a picture of your gel. You probably don't care about the exact tone of color. In that case, you will go ahead and just convert it into exactly black and white, or grayscale image at least. You don't want to do black and white because that's considered to be already thresholded. So here, a very typical operation you perform from going from a colored image into a grayscale image is to average across the channels. You don't necessarily just pick one channel, right? Because picking one channel suggests you only pick that color component, and in case it's not perfect grayscale image, you have to just favor one channel over another for no good reason. By taking average, you conserve, or you preserve all the information that's present in your image to the best of your ability, not giving any particular favoritism over one channel over another. And you take the average, not the sum, because you want to make sure this stays within the range of valid values. Although for grayscale image, we already know that we could take whatever we want, but typically even on the grayscale image, you do want to keep values either between 0 and 255 for integers, or 0 and 1 for floats, at least later on for convertibility sakes. So here, I just take mean across axis equals 2. So here it's 0, 1, 2. So this is indeed the last axis. And if I did that, if I were to look at the shape, it does actually now get the only first 2. So the height and the width, so it's 256 by 256 image. And if you now plot it, now it shows in color because it just started using the default color map because this is now a grayscale image. So of course, if I were to just replace, well not replace, but actually add a specification of the color map as a gray, it should look identical to what it looked before. Okay, question thus far. So far, hopefully it makes sense. Okay, now I'm trying to basically do thresholding, right? So remember the thresholding, you just pick values that has high intensity higher than a certain value. I mean, looking at this, like any reasonable person will probably say, well, if I want to just come out and just get the pixel that is bright, I'm just going to threshold it. I'm going to pick a number, any value that's higher than that, I'm going to start considering that's a part of the foreground. So you can arbitrarily pick. I mean, here, for example, you can actually say, okay, I can say plot and add the color bar. Maybe that give me some idea. So here I'm basically just looking at this and guessing, okay, maybe I can use threshold of 100, right? I mean, even maybe threshold of 50 could work, I'm thinking, but maybe 100. Okay, a better approach is not to just estimate like that all the time. If you can try to get a bit better idea of how different colors are distributed across in terms of intensities, you should try to look at that and make use of that information. So whenever you hear the term distributor or distribution, you better be plotting a histogram. So here what I do is I take my image and I simply flatten it out. So now this is a 2D image, but I flatten it out into a long vector of pixel intensities because when I'm just looking at the histogram over intensities, I don't quite care about the structure of the 2D-ness. So I use Revel to flatten it out. Remember the Revel function on NumPy array flattens it out. And then I pass it into histogram so you can just tally up the values and give you a histogram to have a representation of the distribution. And this is what the intensity distribution looks like for this particular image. You can see there are two humps, one occurring around, say, 2025. That's pretty dark. That's probably where most of the backgrounds are occurring at. It's not completely silent in between. There's some pixel that pretty much covers the entire range. But then there's another huge hump occurring around 230 or so. 230, 240, roughly in that range. And that probably corresponds to most of the pixel that actually is the foreground. So if you were to threshold this, to try to divide basically the left cluster of intensity from the right side cluster of intensity, you will pick value anywhere probably like as close as in between as possible. So maybe I said something like 125, right? Which happens to correspond to roughly the midway value of a possible range of 0 to 255, but at least this is more informed, right? Now you have made a bit more informed decision of what your threshold ought to be. Now, if you're really interested in this, this is where you can apply stuff like cluster analysis, where you can try to describe this distribution as being formed from two separate clusters, and you can even theoretically argue what is the best threshold to apply if you want to have the highest possibility of getting your answer correct. You can go into this. There's some mathematics behind that, something I also do work all the time on. But here, at least, it's fairly straightforward. I think 150 sounds pretty reasonable. 125 sounds pretty reasonable. So I take the threshold value of 125. I threshold the image against it. I pick every position that's higher than 125, and I'm going to call that the mask. And here I'm basically showing two things, image and mask. Notice this is where I was saying, like, if you're only going to do it twice, then probably not going to use any elaborate structure over your code. So I'm just doing subplot. I'm fine writing something that looks similar enough twice. So I do a side by side. And this is what I get. I mean, given the fact that this was already very well separated image, you don't really see that much difference between the original image, which is not showing grayscale right now, but it's showing under some color map. So if I actually want to get back to grayscale, I can go ahead and put the CMap gray. And on the right side is the mask. Again, I could also put this in CMap equals to gray, so it's showing it will show in white and black instead of yellow and bluish color. I mean, there's really not that much difference between these two images. So that suggests that this was already fairly well separated between foreground and background. Now, the final step is like, okay, so I already thresholded it. So I'm claiming that anything that has value of 1 in this mask, or true, since it's actually Boolean, but effectively it's the same thing as ones. those correspond to actual foreground position in your image. And anything that's 0, that's just a background. I'm not going to worry about it. Oftentimes, after you do that and you see these lumps of pixels, you want to actually label and count them up. Or you actually want to say, like, okay, I'm going to treat any connected pixels, like this forms one colony, that's yet another colony, so on and so forth. And that's actually called cluster assignments or contiguity assignments. And there's a bunch of algorithms involved with it. Oh no, you don't have to implement it. This is actually another thing, is that whenever you encounter problems that you think is not too far-fetched, like wanting to know different lumps of data, you probably shouldn't start immediately writing your own algorithm. I mean, it's fun, I get it. I mean, I enjoy writing my own algorithm all the time, but at the same time, you're also trying to get something further down than that achieved by your research and analysis. So coming up with your own algorithm all the time is maybe not the best use of your time. So whenever you encounter situations like this, what you would do is Google for this, right? Just Google, say something like Python. You can even maybe throw in like NumPy or SciPy, but usually just say Python image lumps or Python image lumps assignments, contiguous cells, something that hits and seems to be related. And usually after a couple searches, and you get better and better over time, you find the function that actually gives you contiguous cells or contiguous pixels is function called label in the image. So basically I take the mask, which is in zeros and ones or trues and false, and pass it into this method, a function called label, and it returns two things. So this is actually, you should really actually just be looking at the documentation for it, right? So if I did the ND image label, remember you put just a question mark at the end, and what it will show is that, sorry, let's put this in. What it would show is that, okay, it expects an input. Input will be array-like, object to be labeled. So here's saying any non-zero values in the input are counted as features, and 0 values are considered the background. So that should be pretty straightforward, basically. If it's 0, it will consider background. Anything else, it will be part of the foreground. And structure, you're basically not going to pass in, or this is something you can learn what exactly it would do, but is optional. So if you look at what it returns, it says an integer ND array where each unique feature in input has a unique label. So by feature, they will mean something contiguous by default. And this is something, if you look through it, they will suggest that they will have sense of connectivity. So here it says, has this definition of square connectivity to define and identify things that are considered to be connected. They'll put them up together and count that as one feature. So I want to know it will return two things. One is the label that will basically assign at each point of your, assign that it will return basically same thing as same shape array as the image you passed in, but at every point it will have a number to indicate which group that pixel belongs to. So all the pixels that have same value now correspond to one group. Okay? And num feature is simply a number indicating how many of such features you found. In this case, how many clusters or how many of these colonies did it find in your image. Okay, so and then it goes on to more examples of how to use it. That's kind of the theme throughout many of these documentation. So with some rough idea of how a label could work, you give the mask. Again, it returns two things. So one is the actual label, and another one is the number of the label. So here I just roughly given the name like label in, because I know this is going to be same shape as the original image. And the next one is just the number of the labels. And if I look at the number of labels, at least it has identified 27 features or 27 groups. And if you were to plot the label image, this is something like you could get something like this. So basically, it has used a color map to map different integer values, which will correspond to group assignment, into color. And it should be the case that every group has different color, but some of them are very close. It's a bit harder. But at least you can tell that it has assigned your clusters or lumps into different groups. And if I want to specifically extract one feature out of this, I can take my label image and say, I want to find the one that just, I don't know, someone pick a number between 0 and 27. 24. All right, so label equals 24, and I say plot I'm show, label equals 24. That now gives me a mask for the 24th, or group with ID 24. And you can continue to do this. And this way now, of course, you wouldn't do it manually for every single one of this, but at least you test it out a couple times manually, and you get an idea of how to get access to 0, the first, so on and so forth. And you can do operations like, okay, how many pixels belong to this? In fact, I can already answer that question. For this index 24, if I take that group, I'm just going to call it group, it's zeros and ones, well, it's trues and false, which is, again, effectively ones and zeros. If I just take the sum, then that means I'm taking sum across all the true pixels, aka that's number of pixels that belongs to that group. So if I take a group sum over this, that gives me how many pixels are part of that group. So in this particular image, there's 753 pixels that belong to that group right there. Does that sound about right? That sounds a bit more than expected. I guess that's about right, though. Anyway, so that's actually as much as I had. I was kind of afraid that I'll probably have too much, but I guess I covered it and it wasn't too much of a rush. So yeah, this is one time where it's like pretty good amount of content. So I did actually mean to try to leave enough space at the end, so that also even worked out perfectly for that regard. I was like almost convinced that I'll be saying like, okay, I'm gonna cut it at this point, the rest you can see, and then we want to talk a bit about what's coming up. But I finished it. There's not much to add as far as this topic is concerned. And what I wanted to discuss is just basically what to expect in coming the rest of the week. So this is obviously the week in which you're much more front-loaded. We had one lecture yesterday, and you have a lecture today, so it was a back-to-back. And you're not going to have another lecture until Tuesday next week, right? So that's good 1 week pretty much. What I want you to do is that I'm going to try to get you the assignment tonight, if not by tomorrow morning-ish. And the assignment's going to cover topics over what I covered yesterday and today, but also in general about NumPy array and matplotlib. And it's going to be along the line of just repeating something I've done with some twists in it, right? So for example, one thing could be like, I give you a picture like this. You're supposed to identify different groups inside and tell me which one had the largest area, right? Or even more, which one had the largest area, and take that group and tell me the average intensity of pixels, stuff like that. So it'd be all kind of twists on what you've seen. So it'd be not just repeating what I've done, but hopefully it gives you, with the focus being practice on using NumPy and also plotting with the matplotlib. So that would be the expectation. I'll give you at least a week to work on it. In fact, I think that given the last week, I'm probably not going to really give you a homework assignment for it. I'm just going to basically expect you to complete over the course of 1 week in like 10 days or so. Maybe something that you probably want to get it done by Thursday. That's the last session next week. I'm not going to be able to promise that I'm going to be done grading by Thursday if you're going to try to be submitting by Thursday. I'll probably try to get you within a week or two, and you get feedbacks. And even after the course continues, obviously, you can always ask me questions. And that's another thing I did want to talk. Obviously, this is something that may be more suitable as a last session discussion. But I know there are a couple people who wouldn't be quite making it to the last session, so I will also just say it, is that things like the Slack group for this Edgar Sky thing is going to stay. It's not just one-time deal. I intend to actually keep it alive. There'll be website that'll be associated with it. And there I'll be posting not just this session information, still trying to see if I can post videos on it. That's something I'm discussing with the school. But should that not happen, I'll still keep information about the related course, not just Python, but some related topics, some related workshop I run. I run some random workshop once in a while. And I guess one more thing I did want to bring up is that this was obviously one of the first attempts where a student, I'm a student is leading a workshop for other students. Now, this is obviously not new in the sense of like no one has ever done this in any other school. Obviously, this is done in some schools, but the whole thing of this workshop came about because it's not quite something we do here in this school. And I mean, I do these sessions all the time actually within my lab or neighborhood lab, or more informally, more or less, but I do this all the time. And I strongly believe in someone who's slightly more senior, who has a bit more experience having gone through this training as a grad student or even as a postdoc, being able to share what they've gone through, what really helped them to get where they are. I mean, it's not like they're faculty, so it's not like lifelong career advice. but more practical day-to-day, what are the things you want to know, what's relevant for the kind of analysis and research and techniques you do. And I'm really hoping something like this will not be the first and the last time like a student tries to organize a workshop. I mean, it's not that easy. It did take some amount of work for me to put this together. I'm not done yet. I still have to prepare the rest of the material. But basically my point being that I hope that this is something that you've enjoyed so far, and then I hope that you enjoyed the very last week next week. But if you really think something like this is helpful, it would be very nice if you can actually voice the fact that you enjoyed it and you found something like this to be useful to the department and to the school in general, and try to promote like actions like this, and maybe start to think maybe what are the kind of workshop that will be useful. I mean, I'm glad/sad to say I'll be leaving this year, so I'm not so much going to be able to do another workshop like this next year. I'll be coming back and forth, so it's not impossible, at least, but I'm not around all the time. But in the still leftover time, or at least when time coordinates, I'll be happy to do other workshops. So I've already alluded to many other topics that I find very interesting. I work all the time. I don't only work in Python, I work with MATLAB, I work with C++, I work with a bunch of other languages. I'll do a lot of analysis. I do a lot of neural networks, signal processing, Fourier transforms, whatever, right? Like I work on pretty much a lot of these topics, and obviously I enjoy teaching, so I'll be happy to cover, but that's not everything in neuroscience, by far, not at all. So it'll be good that if you guys start thinking about it and maybe start to think like, how is it that you can maybe communicate interests like this with the department and the school. So that's all I wanted to say. That's the thing I already mentioned about the assignment, so it'll be coming up hopefully tonight, maybe by tomorrow morning, worst case by tomorrow evening. There'll be a link, just like the one you have for the GitHub, where you sign up, and there'll be instructions there. You should be able to clone the repository, put your work in, and then be able to push. So just work often enough, push as many times as you commit, and push as many times as you like. A week or so later on, I'll basically see if you stop being active on it, and then I'll start grading. And so that's also about the assignment. And finally, just to give you an overview of what's going to happen next week. Next session is going to somewhat continue along this theme of image analysis by diving into neural networks. Neural network is not trivial topic, unfortunately. So that means if I have just 2-hour session, I'm not going to be able to make you a neural network expert in any sense whatsoever. But at least what I can do is introduce you to the topic of neural networks, why, or at least what packages are relevant in doing neural networks work in Python, and even with just a little amount of code, how much you can already achieve. I wouldn't be able to give you all the mathematical overviews, like topics like backpropagation and gradient descent. I'm not going to be able to give a due justice on covering the topics, but at least it would be some sort of introduction. Along that theme, you will be getting an instruction video, maybe, at least definitely a document from me instructing you on how to install this one package that's we're going to be using next week for neural network called PyTorch. So far, every package that you've been importing, so you notice something like SciPy and NDImage and ImageIO, you didn't really have to do anything. You just import it as if you expected it to exist. Good majority of them were not something that was built into Python. You got it because you used the Anaconda distribution. Okay? It came with the Anaconda distribution. But as you keep on working in Python, as you become more domain specific, what's in Anaconda distribution is probably not going to be able to cut it. You will want to install additional packages. So I will try to cover this, but this is also one of the most error-prone or like system-dependent issue-prone topic installing new packages are. So at least for the topic of PyTorch, I'm going to give you an instruction ahead, and I want you to try, along with doing the homework, I want you to try installing the PyTorch on your system. And between today and next session on Tuesday, if you have any issues, let me know. I can make myself available so we can work through any issue that comes up, so we can all be at the point where PyTorch is present and functional in your system. And at the beginning of the next session, I will also cover briefly on the topic of what if you want to install some other packages. That's Tuesday. Last session on Thursday will be about data organization. I've been trying to make a point like, okay, like, having a data file itself is not enough. That was my message last week, right? I give you a file, it's not the end of the story. If I give you a file filled with a bunch of numbers, you may not have any idea what I just gave you. And this is a hot topic in data science and any scientific topic really, because sharing data has become like one of the most important concepts, because people now care about stuff like reproducibility of research, right? And openness of research. So sharing has become increasingly important along with sharing your analysis code. But that being said, it's really also not the most straightforward thing to do, because still a lot of people think, okay, well, sharing code is just giving you the file, but maybe without telling you exactly what each and every number represents, or maybe just not giving you enough information. I gave you my raw trace. I don't tell you exactly what the raw trace was about. I don't tell you what is the frequency, like I sampled at. You have no way of being able to process it. So being able to organize your data, being able to organize in a way that it's easy for you to get all the relevant information about it, and also in a way that you can share with each other, is a very big topic. Something I also work very closely personally in the form of, like, say, a company I actually own. So I will cover the topic, and this is, I'm going to at least promise you, it's going to come from like this all open sense of trying to give you an idea of like packages and softwares that you could use to achieve it. I'm not necessarily trying to sell you a product. It's an open source product after all, so you're not going to pay me a cent by using it. But some solutions like that would be useful, one particular one being data joint, and that's going to be a topic I'm going to cover next Thursday, and then would be some conclusion statements. So that being said, there are 2 sessions left. If you have anything that you want me to cover on top of what I just described, this is your last chance to at least make it part of this workshop. So at least I hope you know who I am, and I hope that you know how to contact me. So if you have something that you still want me to cover, maybe the things even I covered, but maybe you felt like a bit more could be added, don't be afraid to let me know. Okay? All right, that was seriously a lot of me talking. I think that's enough. All right, any other questions? You guys didn't have questions so far. Any questions, comments, concerns, complaints? Not yet, huh? All right, that's it.